First it says, what's the electric potential, a distance, okay, so we've got a proton, the distance is 2.5 times 10 to the minus 15 meters, and that's r, the distance away from that proton. You might wonder, where did they come up with this? At 10 to minus 15 meters, that is impossibly small. This is actually about the size, roughly the size of a nucleus. So that's where they're headed with this, is to look at the potential energy of a proton next to another proton, as you might see in, say, a helium-4 nucleus with 2 protons and 2 neutrons. So we want to know the potential, that's V, at this distance away. All right, potential is scalar, so that's nice. We don't have to worry about direction. So this is a distance r, and it's equal to kq over r. Well, for a proton, the charge is equal to the fundamental unit of charge E. So let's rewrite it that way, Ke over r. Now we just need to plug in numbers. K is 9 times 10 to the 9 Newton meter squared per coulomb squared, or yeah, that's right, meter squared per coulomb squared. And then E is equal to 1.6 times 10 to the minus 19 coulombs, all divided by r, which is 2.5 times 10 to the minus 15 meters. Oh boy, okay. Well, 9 times 1.6, for those who don't like to do things in their head, let's just do it this way, this once. 6 times 9 is 54. And so 1 times 9 is 9 plus 5 is 4. So that's 144, and I need to divide by 2.5. So this is 144 divided by 2.5. And then let's take care of the powers of 10. I've got plus 9, minus 19, plus 15. So 9 minus 19 plus 15. This is minus 4 plus 9 is 5 times 10 to the 5th. All right. So 144 divided by 2.5, that would be, well, 50 times 2.5 would be 125. 60 times 2.5 would be 150. So it's just under 60. Let's say, I don't know, 58 times 10 to the 5. Oh, we forgot to do units. This coulomb cancels. One of the meters cancels. We have joules, that's a Newton meter, per coulomb. Alright, so this is equal to 5.8 times 10 to the 6th. You may recognize this as a volt. Potential has units of V. So this should be just a normal thing, and this should be in italics. I can't really do it writing on a board, but just so that you know, the voltage is equal to something in volts. Let's go on to part B. What's the electric potential energy? Now, not potential, this is the energy stored by putting 2 charges that close together, 2 protons that close together. Well, the potential energy is equal to Q times V, which is E times V. Alright, and we've got 1 electron worth of, well, I mean, Q is equal to the fundamental unit of charge. So we might as well just say it's about 5.8 times 10 to the 6th electron volts. That's one way to do it, and we're done. That's the cool way to do it. Another way to do it is if you want it in joules, then you just plug in what E is. It's 1.6 times 10 to the minus 19 coulombs, and we multiply by 5.8 times 10 to the 6th volts, which is a joule per coulomb. Those are interchangeable. coulombs cancel. That's how we get joules. 1.5 times 5.8. Well, look. No, that was 2.5. Shoot. Okay, 1.5 times 5.8 is going to be, let's see, 6, almost 9. Let's say 8.6 or something, times 10 to the minus 13 joules. So looking at it in joules, it doesn't look like a lot of energy. When you compare it to the strength of a chemical bond, which is on the order of 1 electron volt, or 10 to minus 19 joules, you can see that there is a lot of energy stored in 2 protons in a nucleus, at least due to the Coulomb interaction. So if you separated them, they would fly apart really, really fast. All right, that's problem 18.